Hello. What I'm going to do, I'm going to give you a summary of section 1.4. Okay, this is where we end up this week for your quiz. So I talk about the topics on section 1.3 was just introduction of matrices. Okay, so we talk about the operation that we can have, adding, subtracting, multiplying. Okay, and now, before getting to the 1.4, to know that why we need the 1.4, remember our target at the beginning was solving a system of the equation. In order to solve a system of the equation, use the augmented matrix. Now we can use officially the matrix format again and put every given system of the equation into the so-called matrix form, and to see how we can get from there. Okay, so I just finish this interpretation first, and then we get to the section 1.4, which is easy section, but that would give us a notion of the invertibility, which is going to be very important for the rest of the course. So we are going to continue first. This is that's the focus of. So let me just switch it to get this one. Sometimes it's happen. Okay, so let's see if we can change it into this format. Yes, so we got it now. Okay, so this is what we end up. You see, we talk about the operator like the transpose of a matrix. Okay, and we get the transpose as a kind of function with various properties, but the interpretation of the matrix form for a system of the equation is going to be this one. Okay, we did it before, but officially, what is going to be the matrix form? Okay, now that we have enough information about the matrix, so what's going to be matrix form? Because this is the way we are going to operate for the rest of the course. Okay, what's going to be matrix form? Okay, matrix form of a linear system. So we change each linear system into the matrix equation, if you like. Then we can take care of that matrix equation. Okay, so suppose, as usual, we have we'll be given a system that we want to solve. Okay, there you are. So suppose a linear system is given. Okay, a linear system of m equations. That's it, m equations in n unknown. Okay, in n unknown, like the x1, x2 up to the xn, okay, is given by. So create the system as usual. So the system start with like the one that we did before, a11 x1, then a by 2 x2 up to the a1n xn equal to the b1 is the first equation, and then we continue to get to the second one, the second row, first column. So it's going to be second row x2, and continue to get the a2n xn equal to the b2, and then we continue to get to the, okay, remember we have the m equation, so it's going to be am1 xn, then that will take us to the amn xn, and this is going to be equal to the bm. So that's going to be a system of system of m equation in n and no. Now, what we can do, we can use the matrix form if you like. Okay, so write it down into the matrix format, and using the fact that two matrices are going to be the same, see we can end up with this one. So by applying, if you like, by applying a matrix multiplication, applying matrix multiplication. Okay, we can rewrite it as, we get a kind of, we get an augmented matrix or just matrix of a coefficient. If this is going to be matrix of the coefficient, start with the A11, then A12, that take you to the A1n. Okay, and then this is going to be A21. Then we're going up to the A2, okay, A2n, and we continue. The last one is going to be AM, okay, M1, M2 to the AMN. This is going to be a matrix of the coefficient. If you multiply by the matrix of the, okay, the unknown, x1, x2, up to the xn. Remember the multiplication that we have. If you multiply this row by the column, so that give you the first equation. You multiply the second one, you get the second equation, and you end up right at the end. So this is going to be equal to the a column vector, which is going to be the b1, b2, up to the bm. Okay, so that's a system of the equation. We can easily rewrite it down in this format. Okay, the multiplication is all right, because what you got over here, you see this matrix is going to be m by n. Okay, m by n. This matrix is going to be n by 1. Okay, so the middle one is going to be disappear. So the final result must be a matrix of the form of m times 1, or m by 1. Okay, so everything is okay, everything is going to be all right. So what we're going to do is this matrix over here. Okay, this matrix over here, we are going to call it A. Okay, so if this is going to be A, this matrix, altogether the first one is going to be A. The second one will be denoted by X. Okay, and this one will be denoted by a B. So what we're going to do is, we are going to have, okay, so we can write, if you like, we can write the system of the equation as AX equal to the B. So one, it's going to be a matrix equation, if you like. That's a matrix equation where this A is going to be matrix of a coefficient. Okay, that's going to be A1, 1, A1, 2, up to the A1n. And over here, we continue to get to the, okay, to get to the M1 up to the AMN. This is going to be a matrix of the coefficients. And this X is going to be matrix of the unknown, X1 up to the Xn. And that B is going to be the constant matrix, if you like, the constant term. Okay, so that would be the matrix interpretation of the matrix format of the system of the equations. So instead of working with this one, so now you have a matrix equation, then we can solve for X, if you like. We can solve for X in order to get it. It's like, an equation is given to you. You want to find the X. It's the linear equation. In algebra, if you have 2x equal to 5, so X would be 5/2. It's kind of you divide by A. But we don't have the kind of division one. So what we are going to do is, we are going to, in the next section, we are going to introduce a kind of the inverse of a matrix A that will enable us somehow to divide to get the x. Okay, so quickly we can change a system of the equation into the matrix equation, or if this matrix equation is given to you, you can change it to the change it into the system of the equation. So you have some problems in your book that they ask you to do it, so I just give you one. Okay, and from now on we're going to focus on this type of equations. So this is the type that you have. Okay, they ask you to express this is, you have a couple of them in your assignment of this section. So they ask you to express the given system. Okay, the given system of linear equation of linear equations as a matrix equation. Okay, as a matrix equation. The matrix equation is short and easier to handle. Okay, so this is a system. So this is going to be the system x minus 2x2 plus 3x3 equal to 3, okay, or a negative 3. And over here you have the 2x1 plus x2 is equal to 0, and the negative 3x2 plus 4x3 equal to the 1, and we have the x1 plus x3 equal to the 5. Okay, so this is a system of a linear system of the equation, and you want to write it down into the matrix form. Okay, so nicely can be done. Just identify your matrix. Okay, so the solution is going to be, this is going to be the solution. So you introduce, okay, you are going to suppose, get the matrix of the coefficient. This is going to be matrix of the coefficients. You have 1, okay, it's going to be 3 by 3, negative 1, 2, negative 2, 3. The next one, the coefficient of the x1 is 1, there is x2 is 1, there is no x3, that's going to be 0. And the next one, there is no x1. Okay, there is no x1, so this is going to be 0. Okay, 0, negative 3, and we get the 4. And the last one, you get the 1, and this is going to be 0, and this is 3. So this is going to be the matrix A. Okay, this is going to be matrix A. Then the matrix of the unknown, you have, x1, x2, and x3. This is going to be the unknown, and the constant there. Okay, for the constant, we get the negative 3, we got the 0, and 1 and 5. 1 and 5. So eventually, this is going to be ax equal to the b is going to be matrix. Okay, so this is going to be matrix equation of the given system. Okay, so you will see later on that this is going to be your job. Okay, to do this type of problems from now on. Okay, so you have it in your book, in your assignment. This is the way we do it. Okay, so and you have some problems going to be the other way around. So if the matrix format is given to, you can change it to the system of the equations. We did it before, so I give you another one so that you know what's going on when you want to do your problems, your assignment. So this is the other way around. They ask you to express, express the matrix equation, express the matrix equation as a system, of a linear equation. Okay, linear equations. Is the other way around? Just wanted to know that this is not a big deal and you know what you are going to do. So this is a given to you. So you are going to have a 3, negative 2, 3, negative 2, 0, 0, 1. Okay, then you have the 5, 0, 2, negative 2, and this is a 3, 1, 4, 7, and the negative 2, 5, 1, 6. Okay, this is the matrix of the coefficient. It's a 4 by 4. And the matrix of the unknown, it's x1, x2, x3, and x4. And on the other side, you have all zeros. In future, we are going to call this one a homogeneous system. We get the 0, 0. Okay, so this is given to you. This is the matrix. It's a matrix equation. And you want to change it into the system of the, okay, it's a matrix equation. We want to change it into the linear system. Linear system is like the multiplication that we did. Okay, so this is it. Your linear system is going to be, you see the first one is like multiplication. So basically, this is it. It's going to be 3x1, 3x1 minus 2x2. Okay, there is no x3 here. Okay, this is it. Okay, so the first one's going to be x1, x2, x3, x4. So it's going to be plus x4, which is equal to the 0. That's the first one. Okay, and the second one is 5x1. There is no x2, so that gives you 2x3 minus 2x4, which is equal to the 0. And the next one is going to be 3x1. Okay, x2, 4x3, and the 7x4, again equal to the 0. And the last one is going to be negative 2x1 plus 5, okay, plus 5x2, and the x3 and the 6x4 equal to the 0. Okay, so it's the other way around, and just going from one format to the other one, and be prepared for it in, for getting into it and work with this system for future. Okay, so we show that we can change the given system of the equation into the matrix equation. That's a matrix equation. And if the matrix equation is given to you, you should be able to find the corresponding system of the equation. Okay, so that would end up at section 1.1.3. So the next question is going to be for the rest of this chapter, really. And it's going to be with us for the long time. Okay, so the question is going to be, this is it. If you want to solve the system of the equation, you can stay here. You can stay here and nicely solve ax equal to the b. Okay, if you want to solve ax equal to the b, you have to solve for x, like the one that we talk about it. You see, it's like dividing by a, if you like. The dividing, that the division is going to be a kind of inverse of the multiplication. So instead of dividing, we can multiply both sides by something like 1 over a, which is going to be the reciprocal of the a for the numbers. And so what we are going to do is, we call it the reciprocal, or we call it inverse. Okay, so the reciprocal of 2 is what? Is 1/2. But 1/2 can be written as 2 to the negative 1. So what we're going to do is, we are not going to have a kind of division in matrices, but we are going to introduce something like the reciprocal. That something like the reciprocal is called the inverse of a matrix. So if you know the inverse of the A, then you'll be able to find the system of the equation right away. So that's going to be your job in the next two sections, 1.4, 1.5. How we're going to find the inverse of a matrix? First, you have to define what do you mean by the inverse of the matrix, okay? So that's going to be the purpose for the section 1.1.4. So We need more to be, it's like the numbers, you see. When you get a system of the numbers, you do the addition, subtraction, multiplication first, then we get to the division, you stop, and you have a little bit job to do. Okay, so that's going to be the purpose of this chapter, this section 1.4. So we work more with the operation of matrices. We have addition, subtraction, multiplication. So how about a kind of division or the inverse? So we start with some properties of the matrices. Okay, this is it. What is properties of metrics, if you like, metrics operations. So in section 1.3, we define the operations, adding, subtracting, multiplying. Now we can show that this adding, subtraction, multiplications is naturally behave. Naturally behaving means addition must be commutative. Addition can be associative. Any number would have the opposite. So if you have the A, you can have a negative A. So this type of operations that we usually use, multiplication. Multiplication in the case of the matrices is not going to be, is not going to be commutative. But you know that the multiplication can be associative. In the case of multiplication, we can use distributive properties. So these operations are all familiar. Okay, so the properties are going to be, I'm going to use all matrices. So I just listed here. So addition of the matrices is going to be commutative. You see that's the one. That's it. Addition can be associative. So if you have three matrices, you want to add them together, you add the two at the time. Okay, so these are all natural because we're just working on the entries, remember? And the other one is if you have a scalar. Okay, suppose the scalar is going to be CA. We go with the, we go with the alpha or R. I go with the alpha. Alpha is a scalar. So alpha times A plus B is going to be equal to the alpha A plus alpha B. Okay, this is it, where alpha is a scalar, is a number, is a scalar. It's distributive. 2 times A plus B would be 2A plus 2B. Okay, and the other part is if you have two numbers, alpha plus beta, and you want to multiply by A, you can multiply alpha A plus alpha beta A. Okay, so alpha and beta are scalars, numbers. Okay, and some other properties like, if you have alpha times beta, they are numbers. Times A, and you can write down as what? Alpha times beta A. Sorry. It's like 2 times 3x. Would be 2 times 3, then x. Okay, that's one. Then we get a property for the multiplication. Okay, the multiplications are going to be associative. Of course, when you multiply, you must make sure that, you have the size equation in order. So it's going to be AB times C. So this is associative property of the multiplications. It's going to be distributive. So it's going to be A times B plus C, which is going to be, okay, it's going to be AB plus AC. We can distribute. Okay, and eventually we can do it the other way around if you like. So if you have A plus B times C, you can write down as AC plus BC. Okay, but of course, we assume that all sides are going to be all right, and we can do it. Okay, so we just assume that everything is all right. So assuming that when you multiply the sizes of the matrices would satisfy the size equation, the sizes of the matrices. Okay, the size of the matrices are are such that everything would be all right. Okay, such that the indicated operator indicated, okay, operators or operations can be performed, if you like, can be done, can be performed. Okay, you know, so it's natural. All the operation that you have, okay, this multiplication, addition, everything seems to be naturally okay. It's given for the, okay, typically for these matrices. Okay, so this is going to be the result. What else? You know, when you talk about addition, you would like to talk about the opposite of a number. So we need something, we call it zero. So where is going to be zero matrices? Okay, so what is zero? Okay, zero matrices is going to be a matrix whose entries are zero. Okay, so these are going to be a zero matrices, a matrix whose entries are zero. Okay, that's it, a matrix whose entries are all zero, whose entries are all zero, are all zero. Okay, it's called the zero metric. It's called a zero matrix. Okay, so you may have this one. That's a zero matrix. You may have a 2 by 2. It's going to be 0, 0, 0, 0. Okay, or you may have a 3 by 3. Okay, 0, 0, 0, 0, 0, 0, 0, 0, 0. These are the square one. Okay, so it's going to be, no, it's denoted by, it is denoted by just a 0. Or if you like, zero matrix is going to be 0 by, n by n or n by n. That's going to be the zero matrix. Okay. So this is going to be the case. Now that you introduce the zero, it behaves like zero. Okay, so note that it's a nice one. So what do you expect? You expect that if you add the zero to each matrix, okay, and that give you a matrix itself identical. So zero is additive identity. Okay, and you expect that if you get, okay, how are we going to define a minus a? So this is it. You can have a positive a. So a plus a negative a, which is the same as a minus a, is equal to the 0. Okay, and if you multiply the 0 by any matrix, is going to be 0. Okay, that's it. And you have something like a 0 product property, and if alpha a is equal to the 0, then either alpha is 0 or a is 0. Okay, alpha is of course it's going to be a scalar. So quickly we be able to define, okay, to extend all the operations that we have. Okay, zero matrix, so added to any matrix, the result is going to be 0. Enable you to introduce the opposite of a matrix, a negative a. So the 0 is, we can call it as usual as a additive identity. Okay, everything's nice so far. Okay, so that's a zero matrix. Now what else? Now we have, in the case of the addition, 0 is going to be, okay, that is additive identity. So this means if you add any matrix to the 0, the result is identical. So we would like to create something for the multiplication. You know that with the numbers, one is a multiplicative identity. This means if you multiply any number by one, the result would be the number is identical. So 2 times 1 would be 2. 3 times 1 would be, okay, again 3. So what we'd like to do, we'd like to introduce a similar one for the multiplication of matrices. So what is going to be that identity for the multiplication? This is the way we are going to define it. Okay, it's very important matrix. So that's it. What is identity matrix? Okay, so identity matrices, very important one, because we want to find the reciprocal or inverse, so we need this one. So what's going to be identity? Okay, so what is going to be identity matrices? This is it. Identity matrix or matrices. So how are we going to define it? There you are. This is how we're going to define a identity matrix. A matrix. Okay, a matrix, we call it A. Okay, a matrix I, we call it I for identity. So a matrix I equal to, let's say Aij. Aij is going to be a square matrix where I is between 1 and n, and j is between 1 and n. Okay, it's going to be called and n by n identity matrix. Identity matrix. Okay, matrix. If all the entries on its main diagonal is going to be 1, everywhere else is 0. So it's called an n by n identity matrix if, is the way we define it, the Aij, okay, this is going to be equal to 1 for the main entry, for the main diagonal. So it's going to be if I is equal to the j. So this is the entry A11 is 1, A22, A33, A44, etc. Everywhere else 0, 0 if I is not equal to the j. Okay, so this is going to be the case. Therefore, you see, this is going to be the one. If you want to introduce a 2 by 2 one, if you like, or this is it. In general, you see, this is it. In general, you start with the 1. Okay, we get a 1, 0, 0, 0. Then it's going to be 0, that's going to be 1. So you start with the 0, 0, we get 1. Okay, you get it here. So it's going to be 1, 1, 1, etc. So this is going to be the case. Anywhere else it's all zeros. Okay, so this is going to be the I, or I is equal to, you see this is 1. So this is going to be 1, 1, 1, 1. Everywhere else is going to be 0. Okay, and so it's going to be the case. It is denoted by I equal to the simply in, okay, or I equal to the n by n. Okay, so these are going to be, okay, these are going to be the case. And quickly you find out that, so if, okay, if A is Okay, if A is going to be is n, let's say M by n matrix. Okay, if this is going to be M by n matrix, then you can multiply it. A is M by n and by n. You can multiply A times in, which is going to be equal to the A. And if you do this on the other way around, you remember the size equation must be satisfied. And this is going to be the case. Of course, if A is a square matrix, is an n by n matrix, okay, then that's it. A times in is equal to the in times A, which is equal to the A. Okay, so that will emphasize the fact that this is going to be, you see, or if you like, or you have A times I is equal to the I times A, and the result is A. So what we did, we introduced something like 1 in the case of the multiplication. Okay, when we multiply 1 times any number is equal to 1 and the number. So 1 is an identity, is a multiplicative identity. So in this case, this matrix I is going to be a multiplicative identity for, okay, for the operations that we are going to have. So for example, it can be easily seen, okay, can be easily seen that if you have a matrix 2, 3, 2, 3, negative 1, 7, if you multiply by a 2 by 2 matrix, identity matrix 1, 0, 0, 1, okay, so that give you what? That give you 2, 3, 2, 3, negative 1, 7. Now, it can be multiplied easily, you can see it. If you multiply this one, that give you 2, the row column, that give you, okay, 3. If you multiply this one, negative 1 times 1 is a negative 1, and that give you the result. And if you multiply the other way around, that give you the same thing, okay, 1, 0, 0, 1. And if you multiply it by 2, 3, the negative 1 and 7, that give you the same thing. Okay, as you can see, step by step, we're just generalizing what is true for the real numbers or for ordinary operation that we are going to have. We just extend this notion for the, okay, for the matrices. Okay, remember what was the purpose? The purpose was introducing a reciprocal of or the inverse of a matrix. In the case of the number, okay, reciprocal of the 2 or the inverse of the 2 is 1/2, which is 2 to the negative 1. So now that we introduce the I, we have a candidate for 1. So we should be able to find or to define the inverse of a matrix, which is very, very important, okay? So we need that inverse to be able to solve that system of the equation. So that would be quite interesting to introduce the inverse for the first time, okay? Very interesting concept. So what is the inverse? Okay, what's going to be the inverse of a matrix? Inverse of a matrix. That's it. Remember, if you have a number and you have the reciprocal of the number, the product of a number and its reciprocal is equal to 1. Reciprocal of the 2 is 1/2. 2 times 1/2 is 1. So we are going to define a similar one for a matrix. So we replace the 1 by identity matrix. So this is it. We have to have the square matrix to define this. Okay, so if A is n by n matrix, n by n matrix, it must be a square matrix. Okay, if this is going to be the case, then A is said to be invertible. Okay, invertible. That's it. Is said to be okay. That's it. Invertible if there exists if there exists an n by n. Okay, there exists an n by n matrix. Okay, B such that you know that such that what? Such that A times B is equal to the B times A, and the result is going to be an identity, like the one that we talk about it. Okay, it is going to be the case. Okay, it's going to be the case that it's like the product of a number, and it's okay, the product of a number and is reciprocal, is always equal to 1. So AB equal to the BA is equal to the I, and in that case we say that the A is invertible. Okay, it's going to be invertible. Okay, so you know that the I is going to be the identity matrix, of course. Okay, we already talked about it. You know that the I is going to be just n by n matrix. So if this is going to be the case, okay, if this is going to be the case, B is going to be, okay, the matrix B, and the matrix B is called the inverse. It's called the inverse. Okay, it's called the inverse. Okay, the inverse of A. Inverse of A, and is denoted by okay, denoted by A inverse. It's not the power, it's just, we call it A inverse. Okay, it's going to be A inverse. So if A is not going to be invertible, if A has a no inverse, if you like, or is not invertible, if A is not invertible, okay, has no inverse, then it is, okay, it is going to be, it is a singular matrix. Okay, so if it's going to be invertible, you just find it, find the inverse of the, okay, we can find the inverse of the, okay, inverse of a matrix. So therefore, if you like, note that that's what we are going to be interested in. A times A inverse is equal to the A inverse times A, and the result is going to be I. Okay, and that will help us to solve that equation that we talk about it. And in fact, that will help us to be able to define any powers. So the question is how we're going to find this inverse. First, we have to get into the sum. Okay, some examples first. Okay, so we are going to find the inverse all the time. Okay, but sometimes the matrix would be given to you, and they ask you to check. Okay, they ask you to check if that okay, they ask you to check if that matrix is going to be the inverse of the given one. Okay, you have some in your book. So let's try this one first. Example. So suppose you have two matrices. Suppose A is equal to the 2, 9. Okay, 2, 9, and this is going to be 1, 4. And B is equal to, okay, B is equal to a -4, 9, and 1, and a -2. You see this is going to be the one. If this is given to you, we want to show that they are inverse of each other. Okay, if this is going to be the case, then let's multiply them together. A times B, so this is going to be 2, 9, 1, 4. Okay, multiply by a -4, 9, 1, and -2. Okay, let's multiply them together. Remember how you multiply? Row column, 2 times 4, that gives me -8. I just write it down. And then 9 times 1 would be 9. I keep going to multiply this one. 2 times 9 would be 18. Okay, 18 minus 18, which is going to be 0. I multiply this one, that gives me -4. +4. You multiply this one, that gives you, okay, that's going to be 1 times 9 would be 9 minus 8. So the conclusion is going to be 1, 0, 0, 1. Okay, which is going to be the identity. You have to check the both directions. Okay, so let's check the other direction. If we check the other direction, that gives us a -4, 9, 1, and -2. Okay, so that gives you 2, 9, 1, 4. Okay, let's try this one, which is going to be equal to, if you multiply it 9 times 4 times a negative, that gives you -8 plus 9. Okay, row column. Then this one, -36 plus a 36. You multiply this one, it's going to be 2 minus 2. And that gives you 9 minus 8. So the conclusion is going to be, again, we get the 1, 0, 0, 1, which is I. Okay, there you are. So we have the AB equal to the BA is equal to, okay, is equal to the I. So this means they are inverse of the, each other. So they are going to be invertible. And if you like, you can say that therefore B or A, doesn't matter. A is invertible, invertible, and A inverse. A inverse is going to be B, which is, okay, -4, -4, 9, 1, and -2. Okay, so that's just, we are going to see how we're going to find the inverse directly ourselves. But this is just the confirmation. So you have, you have some of them in your book. They ask you to, okay, to prove that they are invertible. So we get this one. Okay, now we need a couple of property of this to check. These type of methods are going to be useful for you. You have a couple of problems. First thing to do that you can prove that the inverse of a matrix is unique. So this means you can only find one inverse. You see, with this method, we confirm it. We are sure that this is the inverse because there is not going to be another one. Okay, so we call it the uniqueness of the. This give you a techniques that would be useful to get to know this for some a specific problem that we're going to have. So we'd like you to get the kind of proof. So the theorem. So this theorem is called uniqueness of the inverse. Okay, that is it. It's going to be uniqueness of an inverse. Okay, uniqueness of inverse. So basically this means the inverse of a matrix is one and only one. Okay, so it's nice to see the techniques. If B and C, if B and C, both of them are both, okay, both inverses of the matrix A, they must be equal to each other. Then B must be equal to the C. That will help us quite a lot for proving something. Okay, so this means you can only have one inverse. You cannot have, you cannot have both, two inverse. Okay, so I'm going to prove both of them are the same. It's a nice proof, you see. So what is going to be the proof? There you are. Let's start with one of them. Okay, so you see this is the way we are going to prove it. It's very nice proof. Since B is, okay, since B is, okay, is an inverse of A, okay, it follows that the definition A times B is equal to the B times A is equal to the I. You see that's going to be the one. Okay, so I want to use this one to show that B and C are going to be the same as each other. Okay, just pick one of these. It doesn't matter which one is it. Okay, and so this is going to be the case. You see, note that, or therefore. You see, I have the B times A is equal to the I. Okay, so what I'm going to do is I'm going to multiply both sides by C. If you multiply both sides by C but from the right, that gives you BA times C, and this is going to be I times C. But I can use associative property. Remember, I can move these parentheses, so that give me B times AC. And since this is identity, that give only C. But remember, C is also an inverse of A. Okay, so but C is also an inverse of A. And so you see AC is equal to the CI, AC is equal to the I. So if you substitute here, okay, so if you substitute here, so I have the B times AC equal to the C. So we substitute I. So that gives B times I is equal to the C. Okay, so B times I is just B. So you get B equal to the C. And you're done. See, very, very nice proof. So I want to prove that if you get one inverse, you see, the inverse of a matrix is unique. So B is an inverse of the A, so it is satisfied. Okay, so this means BI, it's the same for the C, you see, AC equal to the CB equal to the I. So what I did is BA is equal to the I multiply both of them from the right by C. Then I put the A and the C together, but C is inverse of A, so AC is I. So B is equal to the C, and the inverse of the matrix is going to be unique. Okay, so the conclusion is going to be therefore, okay, B is equal to the C, and both of them are going to be equal to the A inverse. Okay, so that's, it's a kind of nice proof. The inverse is going to be unique. Now, we are going to use the same one to prove another great theorem. And this next theorem will tell you that if two matrices are going to be invertible, their product is also invertible. This is going to be very useful. We are going to use it several times. So what's this theorem? This theorem is, what is the inverse of products? Okay. So what we want to prove this, we want to show that, okay, if A and B are going to be invertible n by n matrices. So if you have two invertible matrices, then their product, then AB is also invertible, okay, the product. And in fact, this is how we're going to find the inverse. And if you want to find the inverse of the AB, it's like the transpose. Is the B inverse times A inverse. You see, that's what. It's going to be used. You can use it anytime you like. Okay, anytime you like. If you want to find the inverse of A times B, you switch. B inverse, A inverse. How are we going to prove it? It's very easy to prove. You see, B inverse, A inverse is the inverse of AB if their product is I. You see, this is the inverse of a matrix if their product is going to be identity matrix. So multiply to show it. Okay, it's very easy to show. See, that's going to be the one. Proof, multiply. Look at this one. So I got the AB. Okay, it's going to be IB. I multiply by B inverse, A inverse. If this product is I, they are inverse of each other. So how are we going to multiply it? Remember, the multiplication is associative. So I'm going to put this B inverse and the B together. See, it's going to be A, B, B inverse, A inverse. See? But this is I. Okay, this is going to be equal to the I. Okay, so what I have is going to be A, I, okay, A inverse. But you know that I is like 1. So A times I would be A. But the A times A inverse is like 1 is identity. That's it. Okay, so, but you have to have the multiplication two-sided. So you have to check the other way around too. You see the other way around, how about B inverse, A inverse times AB? Again, associated property, this is a B inverse. You put the A inverse A together times B. This is I. So that gives you B inverse IB. okay? And this is going to be B inverse B, which is I. That's it. You see, we talk about it. If the product of two matrices is I, one of them is inverse of the other one. So this basically means, that the inverse of AB, the inverse of AE is the other matrix. B inverse, A inverse. So that's a very popular theorem, and you can use it anytime you like, and you better know the proof. Okay, we give you one proof in any quiz or any test, okay, and this would be one of the candidates, okay, and we are going to use it for a couple of more problems in this section too. Okay, so we introduce the inverse of a matrix. Okay, so it's like the reciprocal. Okay, it's like the reciprocal that will enable us to do quite a lot from now on. Okay, this is just a theorem. We haven't given you a method to find the inverse really, okay? It's just we prove that there exists. Okay, we prove they exist. Now how are we going to find it? In order to find the matrix inverse of a matrix, we have 3 different methods that we talk about in 5.1.5, 1.6, etc. But in order to be able to do the job so far, for the 2 by 2, there is a short form of inverse. We give you this short form now. We can wait and give you this one later, but why not? We just give you now, and then we generalize it later. So what is going to be inverse, or how are we going to find the inverse of a 2 by 2 matrix? Then we go to the 2 by 3, 3 by 3 after your quiz. You have one in your practice one, but we just give you the question up to 1.4. So if you give you inverse, we give you a 2 by 2 so far, okay? So what is going to be the inverse of? So what is the inverse? Okay, what's going to be the inverse of a 2 by 2 matrix? Of a 2 by 2 matrix? Okay, that's easy. There's a short form. You can use it anytime you like. Okay, I'll prove it later. So I give you this one. You can use it. So that's it. So the matrix, if you like. Okay, a 2 by 2 matrix. A 2 by 2 matrix. Okay, matrix A, or let's say D, because I want to use the D for this one. Okay, the 2 by 2 matrix A equal to, it's going to be matrix, I write this notation, AB, CD. Okay, this is going to be invertible, is invertible even only if, you see, this product is not zero. Like a cross product, AD minus BC is not zero. This is the one we call it determinant later on, but not now. Okay, that's a condition, and we prove it later. So a 2 by 2 matrix is invertible if this is a kind of cross product. You see A times D minus BC is not equal to the zero. If this is going to be the case, in this case, there you are. In this case, the inverse of this matrix, A inverse, is going to be equal to the 1 over this quantity here, AD minus BC. And what we're going to do here, you see, look at this one. We switch the entries on the main diagonal. So this is going to be D, and this is going to be A. Then we use the opposite sign over here. Is a negative C, negative B. That's it. Very easy. you switch the one on the diagonal and switch the sign of the other side. Okay, it's a negative C, negative, negative B. You can easily prove that this is going to be the case. A times A inverse, and we prove it later to give you this number. So we can use it for the time being because we can have some nice problems, but later on we give you a formula, of course, for the 3 by 3 and anything else. So for example, so far, if we ask you to find the inverse of, okay, find the inverse. Okay, find the inverse of this matrix, A equal to 2, 9, 1, 4. Okay, that's it. So you test it to make sure that it's invertible. So find the AD minus BC is equal to 2 times 4 minus 1 times 9. Okay, so that gives you 8 minus 9, which is a negative 1, is not 0, so it's invertible. So what's going to be A inverse? A inverse is equal to 1 over this number, negative 1. You get the matrix. Okay, you switch the main entry. So this is going to be 4, this is going to be 2, and the opposite sides. Negative 9, negative 1. Okay, very easy. Now this would be negative, so it's going to be minus 4, negative 9, negative 1, 2. Now apply the negative sign, so that gives a negative 4. Positive 9, 1, and negative 2. So that gives you A inverse. Okay, it's going to be negative 4, 9, and 1, and negative 2. Okay, so this would give you the result. So what is going to be the application of this type of ideas so far? That would enable you to define, okay, the powers of a matrix, if you like. So what is going to be powers of a matrix? Powers of a matrix. Okay, so if you have a square matrix, so if okay, if A is a square matrix, you need to have the square to be able to talk about it. Okay, the power. So if you have a square matrix, then we defined the following. A to the 0, as usual, we define it to be 1, but 1 would be I. Okay, that's A to the 0. Then the power, the first power is just A. So the second power, or the A to the n power, is going to be A times n. Okay, A, but n times. Okay, this is going to be the 1. Then if A is all the other property of the powers is satisfied. Okay. So for example, also, if you have A times n times A times m, it's going to be A to the n plus m. Okay, this is going to be 1. We can also define a negative power. If you want to define A to the negative n, you find the A inverse first, then you raise it to the n. Of course, the matrix must be, okay, the matrix must be invertible. It's going to be the case if A is invertible. You know, they are all natural. but we want just to show you that you can define a positive power or you can define a negative power to be able to do this type of operations. Okay, that would be enough, but we need examples. There are some nice problems. Okay, I post another part for you. Okay, probably tomorrow. Some very nice application and example so that you'll be able to solve the problems of the 1.1.4. Okay, we are, when I give you those problems, we are done with the 1.4. The next step is going to be, you see, we can do the problem so far with the 2 by 2 matrix or matrices for the inverse, but we need to introduce a more general term that will take us to the 1.5. So I just want to give you a time to be able to take care of this up to the 1.4. So I try to post another one for you, but just some examples and probably some examples from these examples are going to be very similar to the one that you have on the practice one. Okay, so study this one quickly, so you should be able to do the problems that we have assigned: 1.1, 1.2, 1.3, and 1.4, which is going to be due by Monday. Okay, have a good one. I give you another one before the quiz, and of course I will post your quiz let's say Friday night, so you have the Saturday and the Sunday to work on it, and the Monday, so you can turn in your quiz by the end of the day on Monday. Okay, by the end of the day this Monday you have to give us the quiz and your assignments. Okay, have a good one and take care. Bye bye.